Skin, the largest organ of the human body, is capable of detecting human-environment interactions, like touch. Tactile sensing will also enable future advances in robotics. Some commercial robots have embedded tactile sensors for interacting with users, but these robots lack spatial sensing capabilities comparable to human skin. An ideal skin-like tactile sensor might be flexible, scalable, and capable of mapping applied forces. State-of-the-art approaches are beginning to manifest high signal-to-noise ratio in transmitted measurements, and there are ongoing efforts to simplify the techniques for fabricating these devices. By continuing to explore simple techniques of fabrication, future efforts will lead to scalable skin-like sensors to cover large areas. In this work, we used metallized paper, elastomer, and hydrogel particles to make skin-like arrays of sensors to measure force. Each node of the array possessed a hemispherical soft element which sat above an individual interdigitated capacitive sensing unit. When we applied a compressive force to the soft elastomeric layer, its contact area with the sensing unit increased. Hydrogel particles embedded in the hemispherical elements assisted in increasing the measured effective capacitance because the hydrogel particles had a higher conductivity and dielectric permittivity than pure elastomer. The soft layer of the sensor is simple to fabricate. First, combine powdered sodium polyacrylate with water. Wait 2 minutes for the gel to form. Then, fill the hemispherical chambers of the printed mold with the hydrated hydrogel particles. Pour the mixed Ecoflex into the mold. Finally, wait 30 minutes for Ecoflex to cure in an oven at 60 degrees Celsius. The capacitive scanning circuit interfaced with 2 layers of patterned metallized paper with the X layer stacked on top of the Y layer, thus making a 3x3 grid with each button having parallel, interdigitated, metallized tines. To fabricate the paper-based capacitive sensors, we used laser-based ablation to etch through the conductive layer of metallized paper. An Arduino Uno controlled 2 multiplexers and measured the effective capacitance at each button. To characterize the electromechanical relationship between compression and the measured capacitance of an individual sensor, we tested an Ecoflex-based hemispherical element without embedded hydrogel and a composite hemispherical element of Ecoflex and hydrogel. When applying the same maximum displacement in each test, the hydrogel Ecoflex composites had a higher rate of increasing capacitance for the given ranges of applied force than the sample made of pure Ecoflex. This video shows that the prototype sensing array was capable of measuring forces applied to different hemispherical elements. The variation in the sensitivity stemmed from the uneven distribution of hydrogel particles in each hemispherical element. To calibrate the sensitivity of each sensor, we used regularization to convert the measured capacitances to applied forces. A few simple demonstrations show that the prototype sensing array was capable of measuring a distribution of forces. Case 1 and 2 show that the device can detect the distribution of weights in a box. Case 3 shows that the device can detect discrete weights distributed on the elastomer. In the future, skin-like sensors made of paper, elastomer, and hydrogel particles may aid in measurements of distributed forces or pressures. These sensors have the potential to enhance human-machine interactions or detect damage to structures or vehicles for structural health monitoring of soft material-based systems.